Hi there. Today we're going to look at exponential functions, and we're going to start off and just look at some of their graphs. Now, the parent graph that we use is a y equals 2 to the x, and so I have this starting off with a graphing activity, and you have the note sheet for this, I'm assuming, so you need to go ahead and just, all we're doing is setting up some table of values and plotting points to make our graphs. So I'm going to give you some time. You need to go through the front and back page of your notes and get through all those graphs so that you get a feel for what's going on, and then come back and look at what our notes are for the day. So go ahead and pause it, do your tables and graphs, come back. Okay, so let's kind of summarize what you did with those graphs. So the first thing to note is that we have a parent graph, just like we have a parent graph for a parabola or a square root function or an absolute value. This is our parent graph for an exponential. You know that you have an exponential because you have an x up in your exponent part. There's a variable in your exponent. And so we use a base of 2 here as kind of our basic graph, but that can change. Obviously, you did some of that. You changed that number. So if you just make a table of values, you have to remember that anytime you have a negative exponent, it bumps it to the denominator. So that's why when I have this x of a negative 2, that negative 2 power that I'd put right here, the 2 would turn it into a 4, but the negative bumps it to the denominator, and that's why I end up with a 1/4 here. When I plug in a negative 1, well, a 2 to the first is just a 2, but the negative bumps it to the denominator, so it looks like a 1/2. And so forth. You fill in your table, and this is your nice exponential growth graph. There's these few points here, and you should have noticed this one right here especially. From all of your graphs, they all have that point. That's kind of like, I call it the vertex. It's not really a vertex, but it's that key point that we use that shifts around. The other thing that you should notice is that there is a horizontal asymptote in here, and so we make sure that your graph kind of approaches that axis. All right, so from doing all those different graphs, here's what you should have figured out. As you make this base value bigger, it starts to make your graph increase more quickly, and it becomes a steeper graph. The bigger that number is, the steeper it gets, the more quickly it increases. All right, you should have noticed on the one graph that had a negative here, if you have a negative there, it's going to reflect it just like it does with a parabola. It reflects over the x-axis. And then the weird one, which is on the back page of that, is when you have a negative exponent. So if this is a negative exponent right here, now that's actually the same thing as taking that 2 and bumping it to the denominator and calling it a 1/2 to the x power. So either one of these scenarios, if you have a negative power or if you end up with a fraction that's less than 1 for your base value, both of those are going to do the same thing, and what it becomes is a reflection over the y-axis. That's kind of a new thing for us, is to reflect it over the y-axis. But what that does is that turns our nice exponential growth function that we had on our parent graph into an exponential decay situation. So that's important to remember. If you have a negative exponent or a fraction for a base that's less than 1, then that's going to be exponential decay instead of exponential growth. And it shows up through a reflection over the y-axis. Now, with that, we should be able to do some basic graphing, just knowing what those things do. Before we get too far, though, I wanted to take a minute and just go back to that parent graph and just look at some of the key features of it, going back to chapter 1 when we kind of analyzed the graphs. So let's see if we can do our domain and range. Okay, the domain is how far left this graph goes and how far right. So this thing goes forever left. It ends up gradually going forever right. So our domain is negative infinity to infinity. Your range is how low and how high it gets. And so if you look at this, the lowest this ever gets, well, it starts to flatten out here, and so it's approaching 0. Doesn't quite reach 0, so we do a parenthesis. How high does the graph get? Well, it continues to go forever up, so goes to infinity. All right, so on the intercepts, if you'll notice, it never ever touches the x-axis, so we don't have any x-intercepts. But we do have a y-intercept, and it's that key point. It crosses the y-axis at 1, and that's that spot that we pay special attention to where it goes. As far as increasing and decreasing, this function is continually increasing because it's an exponential growth function. It increases the entire time, negative infinity to infinity. Asymptotes, this is an important one. There is an asymptote. It's a horizontal asymptote right here at 0. So you should have y equals 0 for your horizontal asymptote. And then just looking at the graph, as x goes to infinity, y goes continually up, so it goes to infinity. As x goes to negative infinity, your y starts to level out at 0. All right, let's look at some of these graphs. And the first part of your assignment, this is what you're doing. You're just looking at the function and saying, what would this graph do? So knowing that this here is my parent function, that's the basic function, what's going to happen is I start adding some numbers different places. So for instance, right here, it's just like we did with parabolas or rationals or absolute values. If it's grouped with the x, it's going to move it left and right, and you always do the opposite. So in this case, that would take my parent graph and it would move right 1. Okay, on this next one we have a plus 4. That's out there at the end, so that moves it up and down. In this case, it's going to move it up 4. And what it's taken is it's just moving everything. It takes all the ordered pairs, takes the asymptotes, everything, it just shifts them. Okay, on this last one I have both things going. I have the x minus 3, so that's going to move it right 3, and then I have the plus 5, so that's going to move it up 5. All right, so now the last two problems on your note sheet there, that's kind of what it was doing. It was moving it left and right and up and down. So you kind of would go back to the graph, the basic graph. This particular one has a base of 2, but if you'll look at your note sheet, that last problem, or of those last two problems, the first one had a base of 3. So then go back to your notes and look at your base of 3 graph and then shift it. On the second one, I think it was a 1/2. So you look at your 1/2 graph and then shift it. All right, so now let's look at what happens when you put a negative on it. We did one of these. We had the negative out in front. Remember that when that negative is out in front, that is a reflection over the x-axis. It flips it upside down. But that's different than when there's a negative here. And so remember that was kind of like turning the 2 into a 1/2. And either way you see it, it's a reflection over the y-axis. So important to note the difference between that. If the x is way out in front, it's over the x-axis. If it's caught up on your variable, on your x, then it reflects over the y-axis. So then on m of x here, it's got a couple things going. It's going to reflect over the y. And it also has this -1, which is going to take it down 1. Okay, the last one. This one's kind of weird. It's got the negative on the x, but it's different when you've got other stuff going on with it. What you need to do in a situation like this, and you have some of these on your homework, you have to take the negative and factor it out of that exponent. So it's really going to look like this. 2 to the negative, and then factor that out. So it's going to be a positive x and a -3. It's important for you to do that so that you get your shifting correct. Because what's going to happen then with this is the negative that you have this negative here, is going to reflect it over the y. Okay, sorry, let me fix that. Reflect over the y-axis. And then, by pulling that negative out, it changed that sign to what we really want it to be. Since it's a -3, we always do the opposite, so it's going to move it right 3, which is not what you would have thought if you would have left it like this. When you did the opposite, you would have thought it was going left 3. It actually goes right 3 because you have to factor the negative out first. All right, so pay attention to that on your homework. There's a few of those. All right, let's take a break from graphing and let's look at a little bit a more algebraic sense with these exponentials. And before we get started, I wanted to introduce you to something that was kind of new. We have a natural base. We use a letter E to represent that. And that base is what's being taken to a power. So we've been looking at like a y equals 2 to the x. Well, 2 is the base there. So what we're talking about is a natural base of E. And E is really like this limit as we start dealing with some numbers, it starts approaching a certain value. And we haven't talked about limits, so that's a little bit beyond the scope of our understanding. But just think of E as a value that's being approached. And so it happens a lot with different things in nature and with formulas that we use. Specifically for us, it's going to be doing some interest formulas. And so it's a value, kind of like you think of pi as just 3.14. E has a value approximately 2.718. We have a button on our calculator that we'll need to find to be able to use this value in our formulas. And typically it's a base, so it's always going to be taken to a power. So what you're looking for is the button that looks like this. It's an E raised to a power. And so you'll find that on the left-hand side of your calculator, it's second ln. So anytime we come across this E in our formulas, we'll know that we have to go type in that second ln to get that value. One thing to just pay attention to, it's a base E, so let's compare it back to the parent graph. So our parent graph looks like this. All right, that's your 2 to the x. How is a graph of E to the x going to look? Well, since E is a little bit bigger than 2, it's just going to be a little bit steeper and start increasing a little bit more quickly there. Not quite as quickly as a 3 to the x, but somewhere between a 2 to the x and a 3 to the x. That's the only thing that would be different on a graph with an E to the x. Okay, let's move on. One of the things I love about this exponential stuff is there's a lot of formulas that really are things that we use in real life, a lot of things that do with money or populations, and a lot of formulas that use these exponents. So here's a very common one. You may have seen it in Algebra 1. We kind of do a little bit with interest when we do Algebra 1. Don't worry if you don't remember it. Let's go through it. Okay, so it kind of looks like a big ugly formula, but A just represents the ending amount. So this compound interest is like when you put money into the bank and you're going to collect interest on that. Well, to compound that interest, that means that you're going to take all the interest that you've earned and then go put it in your account. And when I say you, it's really the bank. They go figure up how much interest you've earned, they put it into your account, and you benefit because now you get to earn interest on that interest that they just put in there. So the more often they compound it, the better off you are because you start making interest on your interest. So that's a good thing to have it compounded. And so it kind of depends how much interest you're going to earn, just depends on how often they compound it. It depends on a variety of things. Let's go through this formula. So the A is the ending amount. That's how much money you're going to have in your account when it's all said and done. P is the principal. So when you're talking about money, the principal is your initial investment. So that first value there is always your initial amount. And then you take 1 plus R is your interest rate. That's always the annual percentage rate, and you always write it as a decimal. So if it was 4%, you'd write it 0.04. N is the number of times that the bank is going to compound that each year. And so if they compound it monthly, you'll put a 12 in for N. If they compound it quarterly, you'll put in a 4. Daily, you put in 365. All right, and then in the end, the exponent part will take that same n value and multiply it by the number of years that you leave that money in the account. So basically, when you take n times t, that's giving you the total number of times they compound your money. All right, so let's use that formula. And here's a situation. So we have $15,000 that we're going to compound quarterly in an account that gets 6.8% interest. How much money will I have in 10 years? All right, so here we go. So I'm looking for the A. That's the ending amount. I don't know how much I'm going to have at the end. P is the principal. That's the initial investment. So that was $15,000. 1 plus R is my interest rate. Written as a decimal would be 0.068. Divided by the number of times it gets compounded in a year. And since it says it's compounded quarterly, that means I will compound it 4 times a year. And then I take that to the 4 times, and we're leaving it in there 10 years. All right, you have to be really careful when you enter these in the calculator because there's a lot of stuff going on there. You have to watch out for maybe nesting some parentheses. So like for this fraction right here, it would be smart to put that in parentheses. The other thing you'd have to be careful of is you'd want to make sure that that's in parentheses up there, or just do it in your head and call it 40. But you'd want to make sure that the entire value of 40 is in your exponent. Now I do want you to try to type that in yourself, because really this is not the hard part, filling in those numbers. It's getting it put in your calculator and making sure that you get the right answer. So take a minute, type that into your calculator, and then tell me what you get. Okay, I should have told you to pause. You probably didn't pause, but here's what you should end up getting. Go ahead and finish it out, but it'd be $29,439.43. And so if I leave that $15,000 in there for 10 years, I almost double my money there. All right, let's try another one. This is another formula, and all these ones that are in a red box, you need to know these formulas. So the previous one was if I was going to compound it multiple times a year. This is if it's continuously compounded, because let's face it, it's not like it's a lot of work for some banker to sit there and compound the interest in your account, because it's all done on a computer. And so really, it could be continuously compounded. Every time you earn 1 cent of interest, that 1 cent goes into your account, and you're earning interest on that 1 cent. Now that doesn't make a huge difference, obviously, unless you had a whole lot of money in there. But let's look at what the difference would be. Last time they compounded it just 4 times a year. Now let's look at how much money you would make if you were continuously getting that account compounded, so that there was no break between compoundings. So you set it up. Now this is that place where I said that E shows up, because if you were to compound it numerous times, you could put in a 12 for compounded monthly, you could put in a 365 because it's compounded daily, or you could put in a huge number for hourly or every minute or whatever. And what that ends up approaching is this formula here that includes an E. And so it's a nice, easy little formula. We kind of call it PERT oftentimes. So compounded continuously, you take your initial investment, you take it times E to the 0.068 times 10. Okay, so there again, I want you to practice. Make sure that you get all of this up here as part of your exponent. E is that second LN button. All right, pause the video, go figure out what you get, come back. All right, you should have gotten $29,608.17. All right, so it doesn't make a huge difference. Over 10 years, I didn't even make another $200 out of it, but I figure, well, that $200 is better in my pocket than the bank's pocket. So it does benefit you to compound continuously. All right, and here's our third formula that you need to keep track of, and it's really kind of similar, and this is one definitely you probably should have seen in Algebra 1. It's just a basic exponential growth formula, and this one has to do with population, but it could be of other things as well. And so the formula sets up here, and again, this right here is the ending amount. So in this particular example, we're talking about a city. And so the population, this would be the ending population of the city. Again, this first value, it's called P sub O, which is anytime you have a sub O, it's your initial value. So that's my initial population. I have 1 plus R. Again, R is that interest rate, or in this case, it's not always an interest rate, but it's a percentage growth rate. And you always write that as a decimal. And T is your time, which can be in years, but also could be in months or minutes if you're talking about bacteria growth or something like that. Any kind of population growth, be it people, dogs, bacteria, whatever, can use this population growth model. All right, I didn't leave us a lot of room to work this one, but there's not a whole lot going on here. So it says you've got a city with a population of 1,000. It's increasing 5% each year. How much will there be in 10 years? Okay, so I'm looking for the ending amount again. The initial amount was 1,000 people. I put 1 plus my interest rate, or not interest rate, my growth rate is 5%, so I write 0.05. And it's to the 10th power because we're checking after 10 years. And so you type that in, pretty easy to type that one in. You're just going to take 1,000 times, and that 1 plus 0.05 is really just 1.05 if you want to just enter it like that. And then you're going to take that to the 10th power, and you end up with 1,628, and it's 0.9 is what that would be. I don't get real caught up on, I know that this is a population, this is the number of people. I can't have part of a person. I won't worry too much about it. If you want to round that up, you can round it up to 1,629 people. But that's what you end up with for your population then. Okay, last example. You want to be able to use a lot of different formulas. Some of those you're going to have to kind of build yourself. I mean, you have to know your formula and you have to put all the numbers in. But other times they're just going to give you a formula that has some sort of exponent in it. In this case, it's got a negative, which means it should be decay, right? Negative exponents mean it will be decay. And so I have this model. It represents the amount of a bacteria. There were initially 7 grams. That's why the 7 is at the front. And we're trying to figure out how much is remaining after T years. And so specifically they say 4 years. So this model just represents the population of this bacteria. So just be able to use formulas that they give you. So I'm looking for my ending amount. I started with 7, e to the negative 0.0045, and my T is 4 years. So if you type that in your calculator, you're going to 7 times, and then you do that second ln, because it's that e popping up again. And then you type in negative 0.0045. But remember that you got to keep that 4 in the exponent also, so take it times 4. Make sure all of that is part of your exponent. And I end up with P equaling 6.88. So it did not decay very much. I started with 7 grams, now I have 6.88 grams. So it's a very slow decay, which you can kind of tell because that exponent is a pretty small exponent. Nothing's happening very quickly there. All right, so be able to do some graphs, know a few formulas, be able to use formulas. All right, go work on your homework. Good luck.